This short video aims to explain a little bit about the use of nullclines in the general lotka-volterra competition model, and it assumes that you're already comfortable with the idea of density dependence and also interaction between two different species. So we see here we're representing population 1 changing over time, and we have an intrinsic rate of increase given by parameter little r, and we have a carrying capacity given by parameter k1. This means that the population is going to grow from some initial condition up to that carrying capacity. We can also consider the effect of another species on population 1, so that as well as the intraspecific competition, we can introduce interspecific competition. We do that by subtracting an additional quantity here, n2. And so what we're really saying here is that species 2 is having the same effect on species 1 as species 1 is having on species 1. In other words, the competition for resources or space that is limiting population growth is equally felt by species 1, whether it's coming from its own species or the other. That's not necessarily the case. We can relax that assumption. Perhaps we need 10 individuals of species 2 to have the same effect as one individual of species 1. In other words, we should be scaling the coefficient of n2 by some factor. We call those factors competition coefficients, and we typically use the terms alpha sub 1, 2, here meaning the effect of species 2 on species 1. So we read these subscripts a little bit from right to left. That would result in us changing our expression for species 1. We've now added this competition parameter alpha 1, 2 in front of the term n2, so that the effect of species 2 on species 1 is not necessarily the same as the effect of species 1 on itself. Competition is a minus-minus interaction in terms of the fitness effects. Species 1 is having a negative impact on species 2, and species 2 is having a negative impact on species 1. And so we can describe that in this mathematical framework by having these reciprocal equations. Now we have species 2 added in, and we have a competition parameter alpha 2, 1, the effect of species 1 on species 2. So we see that these two equations are linked together. In other words, the dn1 dt equation contains the term n2, and the dn2 dt equation contains the term n1. So that expresses that these populations are linked through competition. Just to motivate this with a real example, we're going to keep in mind invasive shore crabs in the US. It's an interesting situation where people have been able to measure some of the components of competition to try and understand why the population ecology is playing out in the way that it is. So here, for example, we're assuming that you require 2 individuals of species 2 to regulate the population growth of species 1 in the same way that just one individual of species 1 would do. And we're assuming that you only need 1 individual of species 2 to have the effect of 2 individuals of species 1. We typically try and chart what's going on in a phase plane diagram. So rather than plotting population of species 1 over time and the population of species 2 over time, we plot the populations of species 1 and 2, where time can be represented as a trajectory in this space from some initial condition moving towards some final condition, perhaps a stable equilibrium or an extinction event, something like that. As we've been studying single species populations, we've come across the concept of an equilibrium point, and now we have to get to that by thinking about those 2 different equations separately. So species n1, dn1 dt can be solved, and dn2 dt can be solved, and those will give us lines or curves in these phase planes, and where those lines or curves intersect, we are identifying an equilibrium point in the system, although we're not necessarily saying anything about its stability yet. We're just identifying where they would be in space. So here's just one example of one of these, we call them nullclines, the solutions of one of the sets of one of the equations in the set, set to zero. How we do that is we just set the left-hand side, dn1 dt equal to 0, and rearrange the right-hand side so that we can get an expression that we can plot in this n1, n2 space. And we see that we get the equation of a straight line. n1 equals k1 minus alpha 1, 2, n2, a little bit like the y equals mx plus b equation. And so we can do the same thing for n2, and in each case we get an isocline in these phase spaces in the n1, n2 space. So the blue line corresponds to the solution of dn1 dt, and the red line corresponds to the solution of dn2 dt being equal to 0. If we just study each of those isoclines separately, then on the blue isocline, everywhere on that line, we know that dn1 dt equals 0 because that's how we define the line. If we move at any point to the right of that line, in other words, if I were to start on the line here and just move strictly to the right, not moving up and down, just changing n1, that has the effect of increasing n1. We see that this is n1 on the x-axis here, so we've increased n1. And if we look at the dn1 dt equation, we know it's equal to 0 at this point, and now we are increasing the value of n1. And so, oops, just jump back. So we're subtracting more from this equation than we were previously, and it was equal to 0 previously. So now dn1 dt is going to be negative to the right-hand side of that blue line. That tells us that if dn1 dt is negative, m1 is going to decrease over time. So that's why we draw the arrows with the heads on the left-hand side. We're moving from right to left. So whenever n1 finds itself to the right of this blue line, that n1 population decreases. And by the same arguments, when n1 is to the left of the blue line, it's lower than its value corresponding to dn1 dt equals 0. And so we are taking away less than we were previously with this minus n1 term. That has the effect of making dn1 dt positive. And so n1 increases over time. We can apply exactly the same logic to the n2 equation that we got by solving dn2 dt equals 0. Above that red line, n2 is bigger than it was, and it causes dn1 dt to become negative because we're subtracting more away. Below the line, dn2 dt is positive, and so we increase. We need to keep in mind those rules about what happens either to the left and right of the blue nullcline or above and below the red nullcline to help us understand what's happening altogether. So, we can draw these nullclines in a variety of different ways, and they correspond to the relative values of the carrying capacities K1 and K2, and the competition parameters alpha 1, 2, alpha 2, 1. There are 4 qualitatively different ways of putting these straight lines into this phase space. In picture A and picture B, the nullclines don't cross in the positive quadrant, and the blue line is always above the red line. The opposite's true in panel B, the red line is always above the blue line, and then panels C and D, 2 nullclines do cross, although reading from left to right, in panel C, the blue line starts above the red line, whereas in panel D, the red line starts above the blue line. However, we already know enough about these nullclines to try and understand what happens in all 4 of these pictures. we know that anywhere above the red line, N2 is decreasing, and above and below the red line, N2 is increasing. Similarly, anywhere to the right of the blue line, N1 is decreasing, and anywhere to the left of the blue line, N1 is increasing. And so we see that if we were to start out here, for example, we are to the right of the blue nullcline and above the red nullcline, so both N1 and N2 would be decreasing. Inside this bit of space bounded by the red and blue nullclines, we are to the left of the blue nullcline, so N1 is increasing, but we're still above the red nullcline, so N2 is decreasing. And so we get a resulting trajectory heading down to the southeast direction, those arrows. And then finally, closest to the origin, we are both below the red nullcline and to the left of the blue nullcline. And so we are increasing in both the N1 and N2 directions, and trajectories head up to the northeast direction. And so what's going to happen in this system is, regardless of the starting conditions, these two populations are going to pass into the space that's bounded between this red and blue nullcline, at which point they head down, they hit the origin, the axis here, meaning that N2 has gone extinct. Following that event, N1 will increase up to its carrying capacity. Over on panel B, similar story, but everything's flipped the other way around. And so once we pass into this middle channel here, trajectories head up in this direction, N1 goes extinct, and N2 goes to its carrying capacity. Over here in panel C, regardless of where we start, we always head in towards this point where the nullclines cross, and so here we have a coexistence equilibrium that's stable. And then finally on panel D, the trajectories starting in these two quadrants here head towards the equilibrium point, but trajectories in these two parts of the space head away from the equilibrium point. And so what's going to happen is, depending on the initial conditions, trajectories will pass close to the equilibrium point, but then we'll move away from it, and will result in a situation where either N1 excludes N2 or N2 excludes N1. Because it depends on the initial conditions, this deterministic model is generating alternative stable states. And so here we've seen how we can put together information on nullclines to say something about the outcome of competition. We see that it's really driven by how these nullclines are arranged in the phase space, and what's really controlling that is the relative sizes of the carrying capacities and the competition parameters. And more formally, we can see that when, for example, K1 over alpha 1, 2 is bigger than K2, and K1 is bigger than K2 over alpha 2, 1, we're in panel A, and we expect M1 to exclude N2. If those inequalities are reversed, we expect N2 to exclude M1. If the inequalities represent the nullclines as drawn in panel C, we expect stable coexistence. And finally, if the nullclines are arranged as they occur in panel D, we expect alternative stable states, multiple attractors are in here. We can either get attracted towards the extinction of species 1 and the carrying capacity of species 2, or the extinction of species 2 and the carrying capacity of species